Okay, so hello everybody. First I would like to thank people from MIT Media Lab and Andorra for organizing this conference and for having invited me here. So my name is Nguyen Huu. I'm a researcher at IRD, which is a French research institute, and I'm working in a team that works on modeling. So I'm not specialized in urban dynamism or architecture, but I work more on modeling methods. So my presentation will not focus on urbanism or smart cities, because I think you know better than me this point, but I will show you what we do in IRD, what are the methods that we develop, and I hope that you will be able to see what it can bring to you. So, So I think it doesn't continue. Ah non. Okay. Okay. Merci. Okay. Thank you. Okay. So to start with, okay. Okay. So. My background is modeling interaction. So I work on complex systems. So basically, I work on simple interactions that give rise to complex patterns. So it's called emergence. So with simple interaction, you will have very complex models. So to show you a very simple example, so this is a mathematical model. So we have two populations, so it's population dynamics, so it's not urbanism. But we have a population in blue that is a host, and a population in red that is a parasite. So it's a very simple model because we have, it's a mathematical model with only two equations. And you can see on that video that it's a special video of interaction of those two populations. So in blue it's the host, and in red the parasitoid. So you can see that if you have a special environment and only those two equations, then you have very complex patterns that are spiral waves here. Okay. So now I will focus more on the models that we develop in Numea. So it's also to show you what we can do with modeling. And it can highlight some methods that we use for conservation of fish, but that's basically the same methods and the same tools that we can use in urbanism or other stuff. So this is a work that we did in the Numea Lagoon in New Caledonia, and it's about the conservation of a fish that is called Dacilus arianus, which is a small fish, which is a damselfish. So New Caledonia is that island, and we worked on a project on fish that live on coral reefs near the town of Numea. So there is a lagoon here, and in the area of the lagoon, there are reefs where live the damselfish. So they live here, and they lay eggs, and the eggs are transported by the stream, and they can hatch in other places, in other reefs. So we need to do some modeling to understand what is going to happen to that population, if it will survive or not. And there is also a small problem, is that we never have enough data. So it's very difficult to see under the sea where are the fish and to collect data. So it's more like a small data approach. We have quite a lot of data, but it's very small compared to what would be needed for a complete study of the area. Okay. So basically, it's a coupling of three different models. So first, we use a physical model of marine stream, and we with this model we feed an agent-based model for particle transport. So the eggs are transported by the streams that are defined by the physical model, and they move to one reef to another. And then after this, we have a mathematical model that allows us to analyze the dynamics of the model, so we can do prediction about the future, the survival of that species using mathematical methods. So the goal of that project was to estimate the effect of connectivity of coral reefs, so how the importance of the transportation of fish from one reef to another to the survival of the whole community. Okay, so this is another model that we did, but it's in Kenya, so there are more human interaction into that. So it's a model of human and animals interaction in the National Park of Amboseli in Kenya. So it's a park in the south of Kenya, near to the Kilimanjaro. Okay, so you can see here the Amboseli area, and the problem here is to define some policies for the park management, both for the conservation of biodiversity, but also for policies for new settlements and human activities. So it's quite a big model because we have animals, we are human populations that are in interactions. So it's based on a lot of data for vegetation, animal census, and the part for the animal dynamics is based on simple mathematical models that have been driven to ABM models. So it's energy budget models that allows to determine the demography of animals and their migration or movement inside the park. As you can see on the left part, there are black dots which represent human activities, so it can be settlements or agricultural plots. And the development of human activities, agriculture, human-animals conflict, is it's very important to understand how what will be the future of the different species, and what we can do for organizing human settlements, which is quite a bit anarchical right now. So we developed a model with this. So this is, so okay, was supposed to move, okay. Sorry, there is a little problem with, seems to, well, I think there is a problem with, okay, that's fine. Sorry. The computer was lagging a little bit. Okay, so this is a model we developed in Gamma. So we can see the movement of animals on the model. And we can test several scenarios for this, depending on how we'll be developing the human activities. And from this, we can find that if for strong human activities, there is extinction of some animal population. So you can see the evolution of some species. I don't know which one, but some of them disappear for strong human activities, and some of them, for weak human activities, there is the persistence of all the population. So this is a model that we did in Gamma and with mathematical modeling also. That allow to predict the dynamics of the animal population according to different scenarios. So now I'm going to talk a little bit of synthetic population generation. So we developed a generator of population. That means that when you have data on a given population, for example, the average income, the number of people in the household, then if you want to do urban simulation, you need to populate this, and you need to create agents with several attributes. And depending on the survey you have, you need to have some structures you need when you generate your population to find the same structure that you find in reality. Okay. So basically, you have a lot of data, and you have a program that runs and that creates a lot of people. And we use that kind of problem for a model of residential mobility in Marrakesh. So in Marrakesh, it's a very fast-growing city, and people will change place when they have a higher income, when their household gets larger. And we did a model using that kind of generator. And finally, I will just present something that we did. Okay. I will present a model that we did for the COP22, which is a conference of parties. That was a major conference on climate. So this is something very similar to what you did do in MIT. So it's an interactive table, like this one. Sorry, the video is not a good quality video. Okay, sorry, it's lagging. Yeah, okay. Okay, so it's basically a model of road traffic. So we realized a road traffic model using sensors to count the number of vehicles and recreating the traffic in Marrakesh. And in color scale, it's the pollution, it's the exposure of buildings to pollution. So it's a coupling of model with traffic simulation and a population model. So this is something that we presented at this conference in front of the president of the UN General Assembly. So that was, I wanted to show you so that's what we do at IRD. So thank you for your attention. I don't have the last slide. Okay, well, thank you.